So today we're going to be looking at the analysis of gases and solutions. So gas and solution stoichiometry, which is the same thing we've been doing, except we're going to involve our equations that we know for gases, our equations we know for solutions, but the concept is the same in that we're always going to need to start with a balanced chemical reaction equation. And always we need to be converting in some way to the number of moles of the substances. And then we can figure out masses of the substances after, or volumes of the substances after. But relating reactants to products, we always relate to them in terms of the number of their moles. So again, for gravimetric stoichiometry, what we have been doing, we always converted mass to number of moles. For gases, we can use volume, pressure, temperature, molar volume, and ideal gas laws. So we can use our ideal gas law equation, PV equals nRT, which then we can rewrite to N equals PV over RT to get number of moles. And at SATP or STP, there's a shortcut. There's molar volume, knowing that the volume at SATP equals 24.8 liters per mole, and the volume of a gas at STP is 22.4 liters. So if molar volume, as a reminder, equals the volume of your substance divided by the number of moles, then you can write this in terms of calculating the number of moles. N is going to equal the volume of your substance divided by the molar volume. And for solutions, we're dealing with concentration. We know that C, concentration in moles per liter, equals N over V. Therefore, if you want to write that in terms of moles, N equals concentration times volume. Okay, so let's take a look at our first example. What volume of water vapor is produced when 1 kilogram of natural gas is burned at SATP, with natural gas being methane? So step 1 is write the balanced chemical equation. Methane, which is CH4, is going to combust with oxygen, O2, and it will produce, this is a combustion equation, always it will produce carbon dioxide and water vapor. As it comes time to balance, we balance the carbons and hydrogens first, 1 carbon on each side, 4 hydrogens on the left, putting a 2 here gives 4 hydrogens on the right. Then counting the number of oxygens, there's 2 oxygens plus another 2 oxygens gives 4 oxygens on the right. So I'll put a 2 in front of the oxygen on the left for 4 oxygens there as well, and now that is balanced. Okay. Next, we know that we have 1 kilogram of methane, but we want to figure out what the volume of water vapor produced is. So what we'll need to do is figure out how many moles of methane we have. So 1 kilogram of methane we know equals 1,000 grams. And then let's divide that by the grams per mole, or multiply it by 1 mole of methane having 16.05 grams. And just to be sure, the 16.05, that's just the molar mass, right? That is, 1 carbon is 12.01, 4 hydrogens is 4 times 1.01 for a total of 16.05 grams per mole, which I know you all know how to do. So we have 1,000 grams of methane multiplied by 1 mole over 16.05 grams, and we would get 62.30530 moles of methane. So we know how many moles of methane we have. We want to figure out how many moles of water we produce, and after we figure out how many moles of water, we can figure out what volume that takes up. Okay, so we have our methane here, 62.3050 moles of it. And let's use our molar ratios. There are 2 moles of H2O for every 1 mole of methane. Therefore, we have 124.610506 moles of water vapor. So this is good. We know how many moles of the product we're looking for we have. And it's at this point we can say, okay, since we know the number of moles of water, we can figure out the volume it takes up. So we can use the ideal gas law to figure that out, or since we know we're at SATP, we can use the shortcut of molar volume equals 24.8 liters per mole. A gas will take up the space of 24.8 liters for every mole of it you have. So using that, we can just take our, I'll write it over here, 124.610506 moles of the water vapor, multiply it by 24.8 liters per mole. Notice moles on top and the bottom cancel out. And your result would be 3,090 liters. To 3 significant digits, we can say 3.09 times 10 to the 3 liters. Okay, so fair amount going on here, but a lot of it is similar to what we have been doing, or what we had been doing before. We just added that last step of figuring out the volume. So just to summarize, we first wrote a balanced chemical reaction equation. Then we figured out how many moles of a substance we had. So since we had the fact that we have 1 kilogram of substance, we figured out how many moles of that substance we had. Then we used the molar ratios from the balanced chemical reaction equation to figure out how many moles of whichever product we wanted, in this case water. We figured out how many moles of water we have. And then it was step 4 that was new. Step 4, using the ideal gas law, or at this for this instance, the molar volume at SATP, to figure out how many moles of how many liters of the substance we have, what volume it is. Now, if you're more comfortable with equations, let's take a look at how to do step 4 using equations instead of in a conversion style. Molar volume is simply the volume that the gas will take up per number of moles. So the volume of your substance per number of moles. So if what you're trying to solve for is how much space your substance takes up, V, then that would equal number of moles multiplied by molar volume, which is exactly what we have in step 4. Number of moles multiplied by the molar volume of 24.8 liters per mole at SATP. Okay, let's take a look at another example. What mass of sodium is required to make 3.25 kiloliters of hydrogen gas at 20.1 degrees Celsius and 90.5 kilopascals? So note, we are not at SATP anymore. We're at a specific temperature and pressure. We start the same way with a balanced chemical reaction equation. I wouldn't expect you guys to come up with this one all on your own, so I'll just give it to you. We have sodium reacting with water to produce hydrogen gas and sodium hydroxide. Okay, is this balanced? We have 1 sodium, 2 hydrogens, 1 oxygen. Oh, we actually have 3 hydrogens on one side. 2 from here, 1 from here. So 3 hydrogens on one side, only 2 on the other. So what we'll have to do is put a 2 here. That would give me 2 sodiums. So I need to put a 2 next to that sodium. It gives me 2 oxygens as well, which means I should put a 2 over here. And if I have 2 oxygens on one side, 2 on the other, now I have 2 times 2 or 4 hydrogens, 2 hydrogens on one side plus 2 hydrogens on the same side. So 4 and 4, we are all balanced. So 2, 2, 1, 2. Okay, so we want to figure out the mass of sodium. We want to figure out this in order to make 3.25 kiloliters of hydrogen gas. So we know we want to make 3.25 kiloliters, or 3.25 times 10 to the 3 liters, or 3,250 liters of hydrogen gas. So if I have liters, that's volume. In order to relate that amount of hydrogen to sodium, I need to convert the hydrogen into moles, because I always relate moles to moles. That's how I relate amounts, moles to moles. So how many moles of hydrogen do I have? Well, since we're not at SATP, we have to use the ideal gas law formula, PV equals nRT. Then solve for n equals PV over RT. And then we'll fill that in for hydrogen. So number of moles of the hydrogen gas, number of moles of H2, equals the pressure times the volume divided by R divided by T. The pressure being 90.5 kilopascals. The volume being 3,250 liters. 3,250 liters. R being 8.314. And you'll be given back your formula sheets for ideal gases when we do exams, just FYI. And finally, the temperature, remember, has to be in Kelvin. So that's 20.1 plus 273.15. So you have 293.25 for temperature. Plug that all in your calculator. You get 120.67909 moles of hydrogen gas. So using the volume of hydrogen gas, relating it to the ideal gas law, you can get the number of moles of hydrogen gas. Now let me move this down one line just to create some space. And what do you want? You actually want to figure out the number of moles of sodium so that you can get the mass of sodium. So let's do that. We have moles of H2. We know that there are 2 moles of sodium. 2 moles of sodium for every 1 mole of H2. So I should have 241.35818 moles of sodium. So that's the number of moles of sodium I have. What is its mass? Well, just multiply by molar mass. So sodium is 22.99 grams per mole. That's moles of sodium. And final result, you should get 5548.8 grams to the correct significant digits. That's 5.55 times 10 to the 3 grams. More commonly, written as 5.55 kilograms. And there you go. So what did we do? Again, we started with a balanced chemical reaction equation. And we had an amount in volumes of hydrogen gas. So we used that and the ideal gas law to figure out how many moles of hydrogen gas we had. Step 3 would have been to relate the number of moles of hydrogen gas to the number of moles of sodium by using the molar ratios. And then finally converting that number of moles of sodium to mass at the end, because that's what we want to solve for. So again, everything's pretty similar except maybe one change step. In order to find number of moles now, we had to use the ideal gas law formula. Okay, so that's a couple of gas examples. Let's look at a solution one. Here we say that we want to determine the mass of the precipitate when 50 mils of a 1 mole per liter sodium sulfate solution reacts with 25 mils of a 1 mole per liter of barium nitrate solution. So what's the chemical reaction equation for this? This I think you should be able to do on your own. And just to save some space, I want to write that balanced chemical equation above that example line. So we'll write it up here. We have sodium sulfate, Na, and SO4 for sodium. And that's reacting with barium nitrate, Ba, and O3. What's it going to produce? Those are two compounds. Metals are going to replace metals because that's a double replacement reaction. So you'll have the sodium with the nitrate, and you'll have the barium with the sulfate. Now these are all ionic compounds. Let's make sure we're writing them correctly. Sodium has a +1 charge. Sulfate has a 2- charge. So we need 2 sodiums to even out those charges. So Na2SO4. Similar story with barium nitrate. Barium is a 2+, whereas nitrate is a 1-. So you'll actually need 2 nitrates. So we'll put brackets around the nitrates, put a 2 right there to show that we have 2 nitrates to have the charges balance. Sodium nitrate, sodium is +1, nitrate's -1, that's all good. Barium sulfate, barium's 2+, sulfate is 2-, that's all good. And now time to balance the equation. We have 2 sodiums on one side, also 2 nitrates on one side. If we just put a 2 in front of sodium nitrate, that's going to take care of our balancing. So what do we want to figure out? We want to figure out the mass of the precipitate. We'll have to use our solubility table, and using that we'll see that sodium nitrate is very soluble, barium sulfate slightly soluble, so barium sulfate, that is your precipitate. So you want to figure out how much barium sulfate you have when you're given information about sodium sulfate and you're given information about barium nitrate. So let's use that information to figure out how much barium sulfate we should have produced. Now we're dealing with solutions, and what we're given is a volume of a solution and its concentration. So just recall, if concentration equals N/V, then number of moles is going to equal V times C, or volume times concentration, or you can say concentration times volume, whatever. But N equals volume times concentration. Let's look at sodium sulfate. We have 50 milliliters of 1 mole per liter solution. So the number of moles is going to equal its volume in liters. So not 50 mils, but 0.05 liters, multiplied by its concentration of 1 mole per liter. Whereas the number of moles of barium nitrate is its volume in liters, 0.025 liters, multiplied by its concentration of 1 mole per liter. So for sodium sulfate, you have 0.050 moles, whereas for barium nitrate, you have 0.025 moles. So we have a chemical amount of both reactants. Which one's limiting? Well, usually what do? We divide by the coefficients. In this case, both of them have a coefficient of 1, so it'll be the same. It'll be the same result. So 0.05 divided by 1 is just 0.05. 0.025 divided by 1 is just 0.025. So we can just look at the numbers themselves and see that there's less barium nitrate, so this is limiting. Which means we're going to use the barium nitrate chemical amount or mole information to figure out how many moles of barium sulfate we have. Okay, so let's do that. We have 0.025 moles of barium nitrate. And, it's a 1-to-1 ratio. So if we have 0.025 moles of barium nitrate, we also have 0.025 moles of barium sulfate. And that's a 1-to-1 ratio, so we didn't have to do any calculations for that. And if we want to figure out the mass, since we have the number of moles, we'll just multiply that by the molar mass, which I know you can figure out on your own. It's 233.4 grams per mole. So at the end of the day, you'll get 5.835 grams of barium sulfate, which you would round to 3 significant digits, 5.84 grams as your final answer. So same thing, we had a balanced chemical reaction equation. We figured out how many moles of the reactants we have. In this case, since we had an amount for 2 reactants, we had to figure out what the limiting reactant was, and then use that number to figure out the moles of the product we were trying to figure out. And then if we have that number of moles, we can figure out the number of grams. So same concept, the only twist is now that we're dealing with solutions, we have C equals N over V, which you can change into N equals V times C in order to calculate the number of moles you have. Okay, last example. What volume of a 0.25 mole per liter, so that's the concentration, what volume of that concentration of hydrochloric acid would you need in order to react with 14 milliliters of a 0.5 mole per liter sodium carbonate solution? Okay, so hydrochloric acid, HCl. We're going to mix that with sodium carbonate, NaCO3. Note that Na is +1, carbonate is 2-, so we need 2 sodiums to write that equation correctly. And what is going to be produced? You can think of that as a double replacement reaction with 2 compounds. So the hydrogen is now going to be with a carbonate. So we'll need 2 hydrogens there. And the sodium is going to be with the chloride, and that's a +1 - 1, so it's fine written as is. In terms of balancing, I see 2 hydrogens on one side, so I'll put a 2 on the left to get 2 hydrogens. That also gives me 2 chlorides, so I'll put a 2 on the right for 2 chlorides, which also gives us 2 sodiums, and we already have 2 sodiums, so we're good. So now we have a balanced chemical reaction equation, and we have as our information, we have 14 milliliters of 0.50 mole per liter concentration. But what we want to figure out is how much hydrochloric acid we need. Well, if we have 14 mils of 0.5 moles per liter, we can figure out the number of moles. Number of moles, again, is just going to be concentration times volume, or just the way I've written it, volume times concentration. So let's do that. Volume in liters, 0.014 liters. Multiply that by the concentration of 0.50 moles per liter, and the result would be 0.0070 moles, and that is the number of moles of sodium carbonate. Okay, so from the volume and concentration of your sodium carbonate solution, you figured out how many moles of sodium carbonate you have. What you want to figure out is the volume of hydrochloric acid. So figure out how many moles of hydrochloric acid you have. We'll use molar ratios. So there are 2 moles of hydrochloric acid for every 1 mole of sodium carbonate. So that shows that you have 0.0140 moles of the hydrochloric acid. So that is the chemical amount, the number of moles of hydrochloric acid that we want, but we want to determine the volume that we need. So let's take it back to concentration equals number of moles per volume. If what we're looking for is the volume, volume equals number of moles divided by concentration. So let's use that. The volume of hydrochloric acid we need is its number of moles, well, we just calculated 0.140 moles, divided by the concentration, which we're told was 0.25 moles per liter. And you can see as a result, we'll get liters. We end up with 0.056 liters, which you can write, if you wish, as 56 milliliters. So again, solution stoichiometry, similar to gas stoichiometry, similar to mass or gravimetric stoichiometry, where the keys are the balanced chemical reaction equation and using molar ratios to figure out or to relate the number of moles of reactants and products. Okay, so balanced chemical reaction equation and amounts are related in moles. Okay, so for homework and classwork, try the following. 296, number 2, and then page 298 and 299, numbers 1, 3, 4, 6, as well as page 303, numbers 1 to 5. Okay, so practice makes perfect. Go ahead and get those done. Thank you. So that's a good amount of work. Know that tomorrow we'll allot a lot of time in class to do that work as well. So try to get a bunch done today, and we'll have a few more questions, and you'll have a bit more time to work on that tomorrow as well. Okay, thank you.